65 million years ago, a rock from space erased the dinosaurs from existence. It left behind a thin layer of iridium in the geological record. That layer sits precisely at the boundary between two eras. Above it, no dinosaur fossils exist. Below it, they vanish into deep time. Now imagine a civilization rose before the dinosaurs. Millions of years earlier, they built cities. They burned fossil fuels. They left behind plastics and metals and concrete. Then they vanished. How long would evidence of their existence survive? Scientists asked this question in 2018, and the answer shocked them. After 10 million years, almost nothing remains. Tectonic plates swallow continents whole. Erosion grinds mountains into sand. Even plastics break down into molecules scattered across ancient rock layers. The further back you look, the less survives. 100 million years erases nearly everything. We have explored less than 1% of Earth's crust. Most of our planet's 4.5 billion year history sits compressed in rocks we will never examine. Something could have existed here. Something intelligent. Something that burned through resources and collapsed and left almost no trace. The Silurian Hypothesis forces us to confront an unsettling truth. We might not be first. If you find this fascinating, hit that like button and subscribe. We begin now. In 1980, a geologist named Walter Alvarez was studying limestone cliffs in Gubbio, Italy. He found something strange in a thin layer of rock. The layer sat exactly at the boundary between two geological eras. Above it, no dinosaur fossils. Below it, they were everywhere. The layer itself was only about as thick as your fingernail, but it contained unusually high concentrations of a metal called iridium. Iridium is rare on Earth's surface. Most of it sank to the planet's core during formation, when the entire planet was molten and heavy elements fell toward the center. Finding iridium in a surface rock layer means it either fell from space or was mined from deep underground and brought up. Both scenarios are extraordinary. We only accept one as possible. Alvarez proposed that an asteroid impact killed the dinosaurs. The iridium came from the asteroid itself. The theory fit. Asteroids contain iridium in much higher concentrations than Earth's crust. An impact would vaporize the asteroid, spreading iridium particles around the globe. Then, those particles would settle, creating a thin layer in the geological record. One moment frozen in rock, one day in Earth's history preserved because something extraordinary happened. The scientific community eventually accepted the asteroid explanation. Case closed. But the iridium layer held something else, something smaller, microscopic metal spheres. They appear in the same layer as the iridium, scattered throughout the rock. Each sphere is perfectly round, formed from molten metal that cooled rapidly. The conventional explanation says these are impact debris, droplets of vaporized asteroid material that condensed in the atmosphere and fell back to Earth. Museums have entire collections of these spheres. They sit in drawers, labeled and catalogued, evidence of the event that ended the age of dinosaurs. Here's the thing about those spheres. Each one is like a time capsule containing information from a civilization 100 million years dead. You just need to know how to read it. This is the part that gets me. We found evidence, catalogued it, stored it, and moved on, never asking if we interpreted it correctly. The spheres have been sitting in museums for decades. What if they're not impact debris? What if we filed away the most important discovery in human history and never looked twice? The metal composition matches what you'd expect from high-temperature industrial processes. Rapid cooling of molten metal in controlled conditions. Foundries produce similar spheres today when metal droplets escape during smelting. The spheres in the geological record could be asteroid debris, or they could be something else entirely. Finding these spheres is like discovering a smartphone in a medieval castle wall. Either your dating is wrong or something doesn't fit the story you've been told. The iridium layer appears globally, not just in Gubbio. Scientists have found it in rock formations on every continent. The same thin band, the same metal concentrations, the same microscopic spheres. Whatever created that layer affected the entire planet simultaneously. An asteroid impact would do that. so would a global industrial civilization reaching peak production before collapse. The iridium concentration is unusually high, even for an asteroid impact. Some samples show levels 10 times higher than models predict. Scientists explain this with variables like asteroid composition and impact angle, but those explanations require very specific conditions, very precise circumstances. The asteroid would need to be exactly the right size, hitting at exactly the right angle with exactly the right chemistry, or the iridium came from somewhere else. Deep mining operations would encounter iridium-rich layers far below the surface. A civilization extracting resources on a massive scale would bring that iridium up. Processing facilities would release it into the atmosphere. When that civilization collapsed, the iridium would settle into sediment layers. It would mix with the remains of whatever catastrophe ended them, natural or self-inflicted. We interpret the evidence through the lens of what we believe is possible. Ancient civilizations didn't mine deep underground, so we don't consider that explanation. They didn't have industrial processes, so we don't look for industrial signatures. But what if we have it backwards? What if the evidence itself should tell us what's possible, not our assumptions about the past? The spheres remain in their museum drawers. The iridium layer sits exposed in cliff faces around the world. Anyone can see it, touch it, sample it. The physical evidence exists. What we lack is the willingness to question our interpretation. Geology shows us that Earth preserves almost nothing over deep time. After 10 million years, evidence degrades. After 100 million years, almost everything vanishes. But some things survive. Metal concentrations in specific layers. Anomalies that don't quite fit the standard model. Microscopic spheres that could be asteroid debris or could be something we haven't considered. The question isn't whether these objects exist. They do. The question is whether we're reading them correctly, whether the story we tell ourselves about Earth's history accounts for all the possibilities, or whether we stopped asking questions too soon, satisfied with the first explanation that made sense. That thin layer of rock in Gubbio is 65 million years old. The spheres inside it have been waiting that long for someone to look closer. The rock layers we can study represent an almost impossibly small fraction of Earth's history. Think about what that means. Every fossil we've ever found, every specimen in every museum, every bone fragment that helped us understand ancient life, all of it comes from less than 1/100th of 1% of species that actually existed. The rest left nothing behind. No bones, no impressions, no trace. Fossilization is not a common process. It's a statistical miracle. An organism has to die in exactly the right place, at exactly the right time, under exactly the right conditions, usually in water, where sediment can bury it quickly. The body has to avoid scavengers, avoid decay, avoid the thousands of ways organic matter normally disappears. Then, that sediment has to harden into rock. Then, that rock has to survive for millions of years without being crushed, heated, subducted, or eroded away. Then, after all that, someone has to find it. Most organisms don't fossilize at all. Soft-bodied creatures almost never make it into the record. Jellyfish have existed for over 500 million years. We have maybe a few dozen decent fossils of them. Everything else dissolved. The same goes for worms, slugs, most insects. Anything without hard parts that can mineralize. Entire ecosystems lived and died and left behind nothing we can hold in our hands. The rock itself doesn't last. Plate tectonics recycles the Earth's surface continuously. Old crust gets pushed under new crust, melts, and reforms. Most rock older than 500 million years is simply gone, melted back into the mantle, or transformed beyond recognition. The entire surface of Earth from 4 billion years ago has been destroyed and rebuilt multiple times over. We have almost no direct record of what the planet looked like back then. The evidence was fed back into the furnace. Even for creatures we think of as well-preserved, the record is shockingly sparse. Take dinosaurs. They dominated Earth for over 160 million years. That's 30 times longer than mammals have been the dominant land animals. Millions of species across every continent. Trillions of individual animals lived and died. We've found fossils of maybe 700 species. 700 out of potentially tens of thousands. Everything we know about dinosaurs comes from this tiny, tiny fraction of what actually existed. Here's another way to think about it. The fossil record is like a book with chapters torn out. You can tell pages are missing by the numbering, but you have no idea what was written on them. You see chapter 3, then chapter 7, then chapter 12. The story jumps. You know something happened between the chapters you can read. You just don't know what. The binding shows where pages used to be. The narrative doesn't make complete sense, but you work with what survived. Imagine trying to reconstruct all of human history, but 99.99% of all documents, buildings, and artifacts were destroyed. You're left with 3 photographs, a handful of coins, and a fragment of pottery. That's what we're working with for ancient Earth. You'd know people existed. You'd know some of them used metal. Beyond that, you'd be guessing how they lived, what they built, what they valued. Most of it would be invisible to you. The absence of evidence wouldn't mean those things didn't exist. It would just mean they didn't survive. The things we think of as permanent vanish faster than you'd expect on geological timescales. Industrial pollution signatures last maybe 10,000 years in most geological contexts. Human civilization has existed for 5,000 years in its current form. The trash outlives the culture, but not by much. A coal power plant produces distinct chemical signatures in nearby soil and water. Give it a few million years of weathering, erosion, and chemical transformation, and those signatures become undetectable. The landscape erases them. Even our most durable materials break down. Consider plastic. We think of it as essentially permanent pollution, something that will outlast human civilization itself. In a landfill or the ocean, that's true for thousands of years. Plastic breaks into smaller and smaller pieces, but the polymers remain. Here's the thing though, those polymers are organic molecules. Give them enough time under geological pressure and heat, and they decompose completely. 10,000 years in most conditions, maybe a few tens of thousands in the most stable environments. A civilization could have produced trillions of tons of plastic 100 million years ago, and we'd find zero trace of it today. The absence of plastic in ancient rock layers tells us nothing. That realization should make you pause. Think about what it means. If plastic doesn't survive deep time, what does? Metal corrodes, concrete crumbles, glass eventually devitrifies and turns opaque, then breaks down. Organic materials like wood and paper vanish almost immediately in geological terms. Even stone structures erode. Give granite a few million years of weathering and it becomes sand. The pyramids won't exist 10 million years from now. The faces on Mount Rushmore will be smooth rock again. Everything we build is temporary. The Earth's surface is not an archive, it's a recycling system. Material gets buried, compacted, heated, lifted, exposed, and weathered away. The cycle repeats endlessly. Most of what happens on the surface gets destroyed before it can become part of the permanent record. Fossils are the exception, not the rule. They represent moments when the recycling process was interrupted, when something got locked away before the planet could break it down. Those interruptions are rare. The gaps in the fossil record are not small missing pieces. They're vast, empty spaces where entire chapters of Earth's history used to be. We can see the gaps. We can measure them. We know approximately when they occurred and how long they lasted. What we can't see is what happened during those gaps. The rock that would tell us is gone, subducted into the mantle or eroded into sediment that formed new rock somewhere else. The story was written, then erased, then written over. This creates an uncomfortable possibility. Absence of evidence is not evidence of absence when 99% of potential evidence has been destroyed. You can't prove something didn't exist by pointing to the lack of fossils. The lack of fossils is the default state. Finding anything at all is the anomaly. An entire civilization could have risen and fallen in one of those gaps, and unless they left behind something that could survive millions of years of geological recycling, we'd never know. The record wouldn't show them, not because they weren't there, but because the record doesn't show most things. That's the problem. That's the uncomfortable foundation we're building on. The fossil record isn't a complete archive with a few missing pages. It's a few surviving pages from a library that burned down. And on that foundation, we're trying to answer one of the strangest questions science has ever asked. In 2018, a climatologist named Gavin Schmidt and an astrophysicist named Adam Frank published a paper with a strange title, The Silurian Hypothesis. The name comes from Doctor Who, a science fiction show about time travel and aliens. In the show, the Silurians are intelligent reptiles that evolved on Earth millions of years before humans. They built cities, they had technology, then they vanished, leaving almost nothing behind. Schmidt and Frank borrowed the name, not because they believe ancient reptiles built cities, but because the question the paper asks is deadly serious. If an industrial civilization existed on Earth millions of years ago, how would we know? That's not the same as claiming one existed. This is critical to understand. The Silurian hypothesis is not a fringe theory about ancient aliens or lost continents. It's a thought experiment, a scientific method for testing our assumptions about what traces a civilization leaves behind. The paper doesn't argue that ancient civilizations rose and fell before us. It asks whether we'd have the tools to detect them if they had. There's a difference. One is speculation. The other is a framework for understanding what evidence means and what it doesn't. The paper was published in the International Journal of Astrobiology, a serious peer-reviewed climate science journal. It wasn't published there by accident. The real purpose of the Silurian hypothesis has nothing to do with ancient Earth. It's about finding life on other planets. We're searching for industrial civilizations on worlds orbiting distant stars. But we've only had an industrial civilization for 200 years. That's our entire reference library. One example, one data point. If we want to know what to look for when we aim our telescopes at exoplanets, we need to understand what markers an industrial civilization leaves in a geological record. What chemical signatures persist? What structures survive? What traces last long enough to be detected millions of years later? Earth is the test case, the only planet we know that had an industrial civilization. If we can figure out what our civilization will look like in the geological record 50 million years from now, we'll know what to look for on other worlds. The ancient Earth angle isn't the point. It's just the most effective way to run the experiment. You can't study what future geologists will find without asking what current geologists might have missed. That's the surprise. This isn't about rewriting human history. It's about writing the user manual for finding civilizations in deep time. The ancient Earth question is just a side effect of the method. But the side effect is what makes people uncomfortable. Because when you start asking how we detect a previous industrial civilization, you have to confront the timescales involved. And the timescales make humans look very small. Earth is 4.5 billion years old. Humans have existed for 300,000 years. Industrial civilization for 200 years. If all of Earth's history were compressed into a 24-hour clock, humans appear at 11:59 and 58 in the evening, 2 seconds before midnight. Industrial civilization is the last hundredth of a second. You wouldn't see it happen if you blinked. Here's another way to picture it. If all of Earth's history were a road trip from New York to Los Angeles, all of human civilization happens in the final inch before your hand touches the Pacific Ocean. You could have stopped for lunch 50 million years ago, spent an hour eating a sandwich, watched the clouds, then gotten back in the car. During that lunch break, an entire civilization could have risen, built cities, launched spacecraft, and collapsed into dust. You missed it, not because you weren't paying attention, but because an hour in Earth's history is a rounding error. The planet doesn't notice. Dinosaurs ruled for 165 million years. Let that number sit for a moment. 165 million years. Humans have been around for 300,000. Industrial humans for 200. Dinosaurs had 800 times longer than all of human history. If they'd invented writing, they could have had and lost the Roman Empire 200 times over. Built it, watched it crumble, built it again. 200 cycles of rise and fall, and we'd be none the wiser. The time scale swallows everything. The Permian period lasted 47 million years. 47 million. That's not a brief window. That's longer than the entire age of mammals. An industrial civilization could have flourished during the Permian for 10,000 years, built cities across continents, burned fossil fuels, altered the climate, then collapsed. The geological record would show a brief chemical anomaly, a spike in carbon, a thin layer of unusual sediment. We might not even recognize it as artificial. We'd call it a natural event and move on. This is what the Silurian Hypothesis forces us to consider. The timescales are so vast that entire rises and falls of civilizations could be invisible, not hidden, just erased by the normal processes of a living planet: subduction, erosion, the slow recycling of the crust. A civilization that lasted 10,000 years is a geological instant, a flash. You need extraordinary preservation to leave a mark that lasts tens of millions of years, and extraordinary preservation is rare. We're not special in time. We're just here now, able to look around and ask questions. 50 million years ago, the planet was just as real as it is today. The continents were in different places. The climate was different, but the sun rose and set, rain fell, rivers flowed, life adapted and evolved and died. It was a complete world, indifferent to whether anyone was watching. 50 million years from now, the planet will still be here. The continents will have drifted, new mountains will have risen, the details will change, but the machinery of geology will keep turning. If a civilization existed during any of those other moments, we'd need more than luck to find it. We'd need to know what to look for, what chemical signatures might persist, what structures could survive, what anomalies in the rock might be artificial rather than natural. That's what Schmidt and Frank were really asking, not whether ancient civilizations existed, but whether we'd recognize the signs if they had. The answer isn't obvious. The answer requires us to think carefully about what industrial civilization actually does to a planet, what markers it leaves, what traces last. The fossil record won't help. Fossils are rare, and fossils of technology are rarer still. We need to look for something else, something that survives when everything else is ground to dust. We're looking for fingerprints. Not literal fingerprints, chemical fingerprints, signatures left behind in rock and sediment that tell us something was here, something did something, something changed the composition of the planet in a way that natural processes alone wouldn't produce. Technosignatures, that's what we call them. The term usually applies to searching for alien civilizations across the cosmos. Radio signals, waste heat, atmospheric pollution visible through a telescope. But the same concept works looking backward through time. If an industrial civilization existed on Earth 50 million years ago, it would have left chemical traces, isotope ratios, synthetic molecules, changes to atmospheric chemistry that got locked into rock. The question is whether those traces would still be detectable today. Let's start with something we can measure right now. Carbon isotopes. Carbon comes in different flavors. Carbon-12 is the most common. Carbon-13 is heavier, rarer, but still stable. Both occur naturally. Both exist in every living thing, but the ratio between them varies depending on where the carbon comes from. Plants preferentially absorb carbon-12. It's lighter, easier to incorporate during photosynthesis, so living matter has a higher proportion of carbon-12 compared to carbon-13. Fossil fuels, coal and oil, are ancient plants, dead biomass from millions of years ago. When you burn them, you release carbon with that same signature, high in carbon-12, low in carbon-13. That signature is like a fingerprint. Nature has one pattern, burning fossil fuels has another. Both show up in rock the same way your fingerprint shows up on glass. The pattern persists even after the hand is gone. Here's how it works. You burn gasoline. The carbon enters the atmosphere. Rain washes some of it into the ocean. Marine organisms, tiny plankton and shellfish, absorb that carbon to build their shells. They die. They sink. Over millennia, their shells become limestone. The rock preserves the isotope ratio. The rock remembers. If you drill a core through ocean sediment, you can see variations in carbon, 13 levels over time. Each layer tells you something about what the atmosphere was doing when that sediment formed. High carbon-12, low carbon 13, something was burning a lot of organic material. Could be wildfires, could be volcanic eruptions releasing methane, could be fossil fuels. The challenge is distinguishing between those possibilities. Natural events can mimic industrial signatures. Volcanoes release carbon dioxide with isotope ratios that look similar to burning coal. Massive methane releases from ocean sediments can do the same. The signature alone doesn't prove artificiality. You need context, multiple lines of evidence, but the signature is the starting point. Carbon isn't the only isotope that matters. Nitrogen tells a different story. Natural nitrogen in soil has a certain ratio of nitrogen, 14 to nitrogen 15. But industrial fertilizer, the kind produced through the Haber-Bosch process, has a distinct ratio. It's synthesized from atmospheric nitrogen, which has more nitrogen 14. If you spread synthetic fertilizer across farmland for decades, that signature seeps into groundwater, rivers, and eventually ocean sediment. Future geologists could theoretically detect that shift, a sudden change in nitrogen isotope ratios in coastal sediments. No natural process produces that pattern at that scale. Then there are the molecules that shouldn't exist at all, chlorofluorocarbons, CFCs. These are entirely synthetic, never produced naturally, not by volcanoes, not by algae, not by any biological or geological process. They're manufactured for refrigeration and aerosols. When released, they drift into the atmosphere. They break down the ozone layer. They also break down over time, degrading in less than 100,000 years. That sounds like a long time. It's not in geological terms. 100,000 years is a blink. If a civilization used CFCs 50 million years ago, they'd be gone, no trace. But if they used them only 5 million years ago, maybe, just maybe, you'd find degraded remnants in ice cores, if any ice from that period survived, which it probably wouldn't. But the principle matters. Some technosignatures are temporary. They vanish completely within a time frame shorter than most fossil records. Plastics are similar. Polymers break down. UV radiation, microbial action, and chemical weathering tear them apart. A plastic bottle left on a beach won't last 10 million years. But it doesn't disappear entirely. It fragments into microplastics, then into smaller and smaller pieces, until you're left with organic molecules distributed through sediment. Those molecules have signatures, chemical structures that indicate synthetic origin. You'd need sophisticated analysis to find them, but they're there, at least for a while. How long? We don't really know. That's the honest answer. Plastics have only existed for about a century. We're still learning how they degrade over geological time. Imagine trying to prove someone was in a room 100 years ago. The furniture is gone. The walls have been repainted. The building has been renovated. But if you know where to look, you can still find their DNA in the floorboards. That's what technosignatures are. Residual evidence that requires knowing exactly where to dig and what to test. Some signatures last much longer. Plutonium-244 has a half-life of 80 million years. That's 80 million years until half of it decays. The other half is still there. Another 80 million years and half of the remainder decays. If you found plutonium-244 in surface rock, concentrated in a specific layer, that would be remarkable. Plutonium doesn't occur naturally on Earth's surface, not in significant quantities. It's produced in nuclear reactors or during weapons tests. Finding it concentrated in a 50 million year old rock layer would require an explanation, an artificial one. The standard geological processes don't put plutonium there. Something else would have. We haven't found that. To be clear, there's no layer of ancient rock with unexplained plutonium concentrations. But the principle is important. Radioactive isotopes with long half-lives could survive deep time. They'd be detectable if they existed. Every time you burn gasoline, you're releasing carbon that's been locked underground for millions of years. That carbon has a signature. It's old carbon, isotopically distinct from fresh plant matter. That signature goes into the atmosphere, into the oceans, into the shells of marine organisms, and eventually into rock. The rock remembers. Even after the cars are gone, even after the roads have crumbled, even after the continents have drifted and mountains have risen and eroded away. The isotope ratio remains. Which brings us to something unsettling. We've found carbon isotope anomalies in rock layers from the Paleocene-Eocene thermal maximum, 56 million years ago, a period of rapid global warming. Ocean temperatures rose 5 to 8 degrees Celsius in just a few thousand years. The carbon isotope ratios from that time look remarkably similar to modern industrial emissions. High carbon 12, low carbon 13. The standard explanation is massive volcanic activity releasing carbon dioxide and triggering methane release from ocean sediments. That fits the evidence. It's consistent with what we know about volcanic systems and methane hydrates. But the isotope signature is unsettlingly close to what burning fossil fuels produces. We assume it's natural because the alternative is unthinkable, because accepting the alternative would require rewriting everything we understand about the history of life on Earth, because there's no other evidence, no structures, no artifacts, no fossils of anything resembling industrial technology. Just that signature in the rock, a fingerprint that could mean two different things. We've chosen the explanation that fits our expectations, the explanation that doesn't require an ancient civilization. Maybe we're right, probably we're right, but maybe we've already found exactly what we're looking for and explained it away. We've explained things away, given natural explanations to patterns that unsettle us. But sometimes the natural explanation is so improbable that accepting it requires as much faith as rejecting it. Let's talk about Oklo. In 1972, French scientists were processing uranium ore from a mine in Gabon, West Africa. Standard procedure. They measured the isotope ratios of the uranium samples to verify purity. Uranium-235 makes up about 0.7% of natural uranium. The rest is uranium-238. This ratio is constant everywhere on Earth, in meteorites, in moon rocks. Everywhere we've ever looked, the Oklo samples measured 0.717%, lower than expected. That difference sounds tiny. It is tiny, but isotope ratios don't vary. They're fundamental. Finding depleted uranium-235 means something consumed it, something used it up. There's only one process that depletes uranium-235 while leaving uranium-238 behind: nuclear fission. The French scientists had discovered a natural nuclear reactor, not a uranium deposit, not radioactive ore, an actual sustained fission reaction that had operated deep underground for hundreds of thousands of years. 2 billion years ago, when Earth was young and the atmosphere was still toxic, the planet had accidentally invented nuclear power. Earth accidentally invented nuclear power 2 billion years before humans. Actually, that's not quite right. Let me try again. The Oklo reactors are like finding a working engine that assembled itself from random parts. Theoretically possible. Clearly happened. But the more you look at the specifications, the more improbable it seems. For a natural reactor to work, you need very specific conditions. High-grade uranium ore concentrated in one location, water flowing through the deposit to act as a neutron moderator, the right geological configuration to contain the reaction without dispersing the fuel. And this all has to happen at the right moment in Earth's history. 2 billion years ago, uranium-235 made up about 3% of natural uranium, roughly 4 times higher than today. That's because uranium-235 decays faster than uranium-238. It has a shorter half-life. Wait long enough and it disappears. 2 billion years ago, there was just enough uranium-235 for a natural chain reaction to sustain itself under perfect conditions. Those perfect conditions existed at Oklo. Uranium ore deposits concentrated by groundwater. Water flowing through the ore acting as a moderator, slowing neutrons just enough to trigger more fission. Heat from the reaction boiling the water away, stopping the reaction until more water flowed in. An on-off cycle that regulated itself. The geologists found 16 separate reactor zones at Oklo, 16 places where this unlikely combination of factors aligned. For a natural reactor to work, you need uranium concentration, water flow, and rock geometry to align perfectly. It's like needing 3 different slot machines to hit jackpot simultaneously. It happened at Oklo 16 times. The evidence is undeniable. Fission products in the rock match exactly what we'd expect from sustained uranium fission. Neodymium isotopes, ruthenium isotopes. The decay chains are consistent with a reactor operating for hundreds of thousands of years. Scientists have studied Oklo extensively. The consensus is clear. Natural nuclear reactors are possible under the right conditions. Oklo proves it. But there's something about the Oklo reactors that doesn't quite fit the natural explanation. Something that's been quietly troubling geologists since the discovery. The geometry of some reactor zones is unusually precise. Natural ore deposits are chaotic, irregular. They follow the paths of least resistance through rock, creating messy, branching formations. Some of the Oklo reactor zones show geometric arrangements that look almost intentional. Uranium concentrated in layers. Spacing that seems deliberate. Boundaries that are sharper than groundwater, deposition typically creates. The scientific explanation is that we're seeing the result of very fortunate geological processes. Fracture patterns in the rock, crystallization boundaries, sedimentary layering, all combining in ways that happen to look organized. That's possible. Geology can create patterns that appear designed. We see faces in mountains. That doesn't mean mountains were carved. Here's the part that's harder to explain away. The water flow through some Oklo reactor zones shows evidence of regulation. Natural water flow through rock is chaotic and irregular. It responds to pressure gradients, seasonal variations, tectonic shifts. It fluctuates constantly, but some of the Oklo reactors show on-off cycles that look almost engineered, regular intervals, consistent duration. Patterns that suggest something was moderating the water flow with unusual precision. The official explanation is geological coincidence. Pressure release cycles in the rock, thermal expansion, creating predictable flow patterns. Steam generation from the reaction itself creating a feedback loop that happened to stabilize at regular intervals. These mechanisms can work. The math supports them. But the patterns have never been fully explained. Not in a way that accounts for the consistency across multiple reactor zones. Not in a way that explains why these particular deposits developed such precise regulation while other natural uranium deposits never came close to achieving sustained fission. Think about what we're accepting as natural. 16 separate locations where uranium concentrated to reactor-grade purity, where water flow moderated neutron flux with enough precision to sustain reactions for hundreds of thousands of years without dispersing the fuel or poisoning the reaction with fission products, where geological structures contained the heat and radiation without fracturing, all happening during the narrow window of Earth's history when uranium-235 was abundant enough to make natural fission possible. The probability isn't zero. Oklo exists. The reactions happened. We have the physical evidence. But the probability is disturbingly low, low enough that if someone proposed it as a hypothesis before we found Oklo, they would have been dismissed, low enough that finding one natural reactor would have been remarkable. We found 16. The question isn't whether natural nuclear reactors are possible. Oklo proves they are. The question is whether our definition of natural is broad enough. Whether we can look at 2-billion-year-old rock and confidently distinguish between a fortunate geological accident and something that was arranged, something that was built. We assume Oklo is natural because the alternative is unthinkable, because accepting the alternative means accepting that nuclear technology existed on Earth 2 billion years ago, before complex life, before oxygen in the atmosphere, before anything we'd recognize as civilization. There's no other evidence. No structures, no waste repositories, no isotopic signatures of plutonium production or enrichment beyond what natural fission creates. Just these reactor zones with their unsettling geometric precision and their unexplained regulation patterns. Maybe that's all there is. Maybe Oklo is exactly what it appears to be. A cosmic accident that produced working nuclear reactors through nothing but geology and time and extraordinarily good luck. Maybe we're pattern-seeking animals finding design where there's only chance. Or maybe we're looking at technology so old that almost every trace has been erased, ground down by tectonic forces, subducted and melted and recycled through the mantle. Maybe the Oklo reactors survived precisely because they looked natural enough that geology preserved them instead of destroying them. We've made a choice about what Oklo means. We've chosen the explanation that fits our expectations, the explanation that doesn't require rewriting the history of technology on Earth, the explanation that lets us sleep at night. But the geometry is still there. The regulation patterns are still there, waiting in 2 billion-year-old rock, and we still don't have a complete explanation for how they formed. We've been looking at evidence that might survive 2 billion years. Reactor geometry, isotopic anomalies, things that could last because they were big enough, deep enough, protected enough by sheer geological luck. But what about evidence in life itself? What about biology as a record keeper? 540 million years ago, something extraordinary happened. The Cambrian explosion. A moment in Earth's history when complex life suddenly appeared in the fossil record. Not gradually, not slowly, suddenly, in geological terms, overnight. Before the Cambrian, life on Earth was simple, soft-bodied organisms, mostly microscopic, some larger things, but nothing with hard parts, nothing with eyes or shells or claws. The fossil record from that time is sparse because soft bodies don't preserve well. What we do find suggests a world of simplicity, single layers of cells organized into basic shapes. That was life for billions of years. Then, the Cambrian explosion begins. It lasts roughly 25 million years. That sounds like a long time. It's not in geological terms. 25 million years is fast. Evolutionary rocket speed. During this window, almost every major animal body plan appears. Hard shells emerge. Eyes develop. Predators evolve. Prey evolves defenses. The fossil record goes from nearly empty to explosively diverse. Trilobites with compound eyes. Arthropods with jointed limbs. Creatures with spines and segments and bilateral symmetry. The biological complexity that defines animal life today all shows up during this relatively brief period. Picture Earth as a garden that had only moss for billions of years. Then, one day, geologically speaking, roses and oak trees and Venus flytraps and redwoods all appear simultaneously. You'd ask what changed. You'd want to know what triggered it. The transformation demands explanation. The standard explanation involves environmental changes. Oxygen levels in the atmosphere increased. Ocean chemistry shifted. These changes created new opportunities. Evolution responded by diversifying rapidly. Natural selection acted on existing genetic variation and produced the explosion of forms we see in the fossil record. That's the consensus view. Most scientists accept this framework, but even within that consensus, there's debate. The speed still troubles people. Evolution is usually a slow accumulation of tiny changes over immense time. Each generation adds small modifications. Beneficial traits spread gradually through populations. That's how it works most of the time. Slow, incremental, patient. The Cambrian explosion is like watching a time lapse where the film suddenly speeds up 100 times for one section, then returns to normal speed afterward. You'd suspect someone edited the footage. You'd wonder why that particular interval ran differently than everything before and after. Evolution is usually compared to a biological arms race, but one that takes millions of years to go from simple weapons to slightly better weapons. The Cambrian explosion went from zero to nuclear in geological terms. It's like going from stone tools to smartphones in a single human generation. The comparison sounds absurd. That's the point. The speed is absurd by normal evolutionary standards. Genetic evidence adds another layer of strangeness. The toolkit for building complex body plans appears to have existed long before the Cambrian explosion. Hox genes control body structure. They're like instruction manuals that tell cells where to form a head, where to put segments, how to organize a body plan. These genes are ancient. They show up in genetic analysis as being much older than the Cambrian period. The blueprints were there, but nothing was being built. For potentially hundreds of millions of years, the genetic instructions for complexity existed in simple organisms that never expressed them. Then suddenly, everything gets built at once. Every major body plan deploys from this existing genetic toolkit in a relatively narrow window of time. It's like discovering that ancient humans had instruction manuals for building smartphones 1,000 years before they had electricity. The tools existed, dormant, waiting. For what? This is where the thought experiment gets interesting. Within the standard framework, we assume those Hox genes evolved slowly in earlier organisms. They were there, doing simpler jobs, and environmental changes allowed them to be deployed for more complex purposes. That's reasonable. It fits the evidence. But what if you approach it from a different angle? What if Earth had hosted a previous civilization, one with biological engineering capabilities, one that understood genetics at a level we're only beginning to reach? They could have seeded the planet with genetic potential, programmed the building blocks for complex life into simple organisms, created a biological foundation that would trigger under certain environmental conditions. You wouldn't need to engineer every species directly. Just establish the toolkit, plant the Hox genes and regulatory networks into early life forms, set the conditions that would activate them, then wait. Let natural processes take over once the foundation was in place. The civilization disappears. The planet recycles their physical traces, but the biology remains, encoded in every living thing that follows. The Cambrian explosion could be evolution responding to environmental changes. Or it could be terraforming on a timescale we can barely imagine, a biological program that ran after its creators were gone. We're not saying that's what happened. We're asking if you could tell the difference. If a civilization had engineered Earth's biosphere 540 million years ago, what evidence would remain? Would genetic sequences look any different than if they evolved naturally? The answer is probably not. Evolution and design can produce similar results, especially after hundreds of millions of years of natural selection modifying whatever came before. The patterns blur, the signatures fade. You're left with life that works, that adapts, that evolves. Whether it started from purely natural processes or from engineered genetic foundations becomes impossible to determine. That's the uncomfortable part. We've made a choice about what the Cambrian explosion means. We've chosen the explanation that fits standard evolutionary theory, the explanation that doesn't require ancient civilizations or biological engineering, the explanation that keeps the history of life on Earth simple and continuous. And that choice is probably correct. The evidence supports it. The science works. But the speed is still there. The sudden appearance of complexity is still there. The ancient genetic toolkit, sitting dormant for vast stretches of time, is still there, waiting in the fossil record and in the genomes of every complex organism alive today. And we still don't have a complete explanation for why it all happened so fast during that particular window. The mystery remains, encoded in stone and in cells, 540 million years old and still asking questions we can't fully answer. We date rocks by measuring radioactive decay. The principle is straightforward. Certain elements are unstable. They break down over time into other elements. This happens at rates we can measure in laboratories. The rates don't change. Heat doesn't affect them. Pressure doesn't affect them. Chemistry doesn't affect them. The decay just happens. Tick, 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 like the most reliable clock in the universe. The measurement itself is called radiometric dating. You take a sample of rock. You measure how much of the original radioactive element remains. You measure how much of the decay product has accumulated. You do some math based on the decay rate. The calculation tells you how long the decay has been happening. That number becomes the age of the rock. Different isotopes work for different timescales. Carbon-14 has a half-life of 5,730 years. Half-life means exactly what it sounds like. After that much time, half of the carbon-14 in a sample has decayed into nitrogen-14. Wait another 5,730 years and half of what remained decays. Then half again. The pattern continues until there's too little left to measure reliably. Carbon-14 works for dating things up to about 50,000 years old. Human artifacts, ice age bones, recent geological events. For ancient rock, we use isotopes with much longer half-lives. Uranium-238 decays into lead-2O6 with a half-life of 4.5 billion years. That's almost the age of the Earth itself. One full half-life spans from the formation of our planet to right now. This makes uranium-238 perfect for dating the oldest rocks we can find. Samples from the deep crust, meteorites from the formation of the solar system, stones that remember when nothing lived here yet. The math is beautiful. The physics is solid. The measurements are precise. But there's an assumption built into every single date we calculate. The system has to be closed. No contamination, no loss of material, no gain of material. The rock formed with a certain ratio of parent isotope to daughter isotope. Then it sat there, undisturbed, while decay happened. Nothing got in, nothing got out. The only thing that changed was the slow conversion of one element into another. If that assumption holds, the date is accurate. If that assumption is wrong, the date is meaningless. Think of it like watching sand fall through an hourglass and calculating when someone flipped it over. You measure how much sand is in the bottom chamber. You measure how fast sand falls. You work backward to figure out when the glass was turned. The calculation is precise. The method is sound. It works perfectly unless someone opened the hourglass and added or removed sand. Then, your calculation is still precise, but it's meaningless. The math didn't fail. The assumption did. Or, imagine you're trying to figure out when a bottle of wine was made by measuring how much has evaporated. You can calculate it exactly if the bottle has been sealed the whole time. You measure the level. You know the evaporation rate. You work backward. The number you get is accurate only if no one opened the bottle and drank some, then sealed it again. The math is perfect. The method is perfect. But the answer is wrong because the system wasn't closed. Geologists know this. They're careful about it. They select samples that show no signs of alteration. They avoid rocks that have been heated or compressed or exposed to groundwater. They cross-check using multiple isotope systems. If uranium-lead dating gives one age and potassium-argon dating gives a different age, something is wrong. The rock has been disturbed. The system wasn't closed. You discard the sample and try again. The science is solid. The interpretation depends entirely on whether nature was the only force acting on the rock. Here's where it gets strange. If an ancient civilization refined uranium for reactor fuel, then disposed of depleted uranium in a geological repository, we'd find that uranium millions of years later. We'd date it using radiometric methods. The isotope ratios would be artificially altered. The uranium-238 would be depleted. The uranium-235 might be concentrated or absent. The ratios wouldn't match any natural formation process. We'd get nonsensical ages that made no sense compared to the surrounding rock. We'd likely assume we made a measurement error. We'd assume contamination occurred. We'd recalibrate our instruments and try again. We might eventually conclude the sample was unreliable and move on. The method is sound, but it assumes nature is the only force that concentrates or depletes isotopes. The same problem applies to any processed material. Smelted metal has isotope ratios that don't match ore. Refined chemicals have concentrations that don't occur in nature. Concentrated isotopes for industrial use leave signatures that look like nothing geology produces. If you didn't know these materials were artificial, if you found them buried in rock layers 100 million years old, you'd try to date them. The dates would be wrong, not because the method failed, because the material wasn't natural. We don't really know if some of the rock we're dating was in its natural state, or if it was processed by industrial means 100 million years ago and then redeposited. That's the honest answer. We assume natural formation because the alternative requires rewriting everything. We assume closed systems because open systems with artificial interference aren't supposed to exist in deep time. The assumption makes sense. It's probably correct, but it is an assumption. The rates of decay are constant. The math is elegant. The instruments are precise. Every part of the method works exactly as physics says it should. What we can't know for certain is whether the samples we measure have only been touched by geological processes. whether the isotope ratios we're reading represent undisturbed natural formation, whether some of the numbers we've calculated are accurate measurements of artificial materials that we've misinterpreted as ancient stone. You date a rock, you get a number. The number is precise to within a few million years. You write it down, you add it to the geological timescale. You move forward with confidence. The confidence is justified. The method has been tested thousands of times. It works. Cross-checking confirms it. Independent measurements align. The ages make sense in context. Older layers are deeper. Younger layers are higher. The sequence is consistent, but consistency doesn't prove naturalness. It proves order. If an industrial civilization processed and disposed of materials in an organized way, those materials would still appear in consistent layers. They'd still have relationships to surrounding rock. They'd still fit into a sequence. The only thing that would be off is the isotope ratios. And when those are off, we assume something went wrong with the measurement. The hourglass looks undisturbed. The glass is intact. The sand is falling at the expected rate. You calculate when it was flipped. You're probably right. Unless someone opened it very carefully, altered the contents, and sealed it so well you can't tell it was ever touched. Then you're measuring accurately but interpreting incorrectly. The method works. The answer is still wrong. That's the uncomfortable space we're working in when we date ancient rock. The science is excellent. The assumptions are reasonable. The results are almost certainly correct. Almost. We've built an entire understanding of Earth's history on radiometric dating, the timeline of life, the age of mountain ranges, the formation of continents, the impact events that shaped the surface. All of it depends on dates calculated from isotope ratios in rock, and those dates are only as good as our certainty that nothing but nature has been concentrating, depleting, processing, or repositioning radioactive elements for the last few billion years. So we've been questioning whether our methods for dating ancient rock might miss evidence of interference, whether isotope ratios that seem natural could have been altered by technology we can't recognize, whether the timeline we trust is actually as solid as we think. There's a place we can test these ideas, a moment in Earth's history so catastrophic, so sudden, and so strange that it demands explanation. And the explanations we have don't quite fit. 252 million years ago, something killed almost everything. We call it the Great Dying, the Permian-Triassic extinction event, the worst mass extinction in the history of complex life on this planet. 96% of all marine species vanished. 70% of all terrestrial vertebrate species died. Think about what 96% means. Picture a room with 100 people. 96 of them die. 4 survive. Those 4 have to rebuild everything. No infrastructure, no knowledge base, no support systems, just 4 people trying to restart civilization from scratch while everything around them burns. That's what happened to life on Earth at the Permian-Triassic boundary. It took 10 million years for life to recover its former diversity. 10 million years. Humans have existed for about 300,000 years. Modern civilization for maybe 10,000. The recovery period from the Great Dying was 1,000 times longer than all of recorded human history. The standard explanation is volcanism. Massive eruptions in what we now call the Siberian traps. These weren't ordinary volcanoes. They were flood basalts, lava pouring out of cracks in the Earth's crust for hundreds of thousands of years. The eruptions released carbon dioxide and sulfur into the atmosphere. Global warming accelerated. Ocean temperatures rose. The warming triggered methane release from the ocean floor. Methane is a greenhouse gas much more powerful than carbon dioxide. The warming amplified. Ocean chemistry changed. Acidification, oxygen depletion. Anoxia spread through the depths. Marine life suffocated. On land, temperature spikes and acid rain killed forests. Food chains collapsed. Everything fell apart. It's a reasonable explanation. The evidence for the Siberian traps is solid. The timing matches. The mechanism makes sense. But there are problems. The speed of the extinction is debated. Some evidence suggests the whole event happened in less than 100,000 years, possibly much faster. The geological record has trouble resolving events shorter than that, but there are hints. rock layers that suggest rapid deposition, fossil beds where species appear and disappear almost instantly, carbon isotope excursions that spike and fall like a fever chart. The boundary layer between the Permian and Triassic periods shows a sharp shift. Light carbon floods the system. The ratio changes dramatically. That's consistent with volcanism. Volcanic carbon has a distinct isotopic signature. The carbon from the Siberian traps could produce exactly that spike. It's also consistent with massive burning. The carbon isotope spike at the boundary looks remarkably like what we'd expect from burning an entire planet's worth of fossil fuels in geological fast forward, which is exactly what we're doing now, and exactly what a collapsing industrial civilization would do in its final resource wars. When energy becomes scarce, you burn everything you can reach: coal, oil, forests, organic matter. The isotope signature would be identical to volcanism. The boundary layer would look the same. You'd see light carbon flooding the system, a rapid input over decades or centuries, fast enough to look instantaneous in rock formed 252 million years ago. There's no way to tell the difference. Not from the isotopes alone. The extinction pattern is strange. It wasn't uniform. Some ecosystems collapsed instantly. Reef systems died almost overnight. Certain marine environments went from thriving to empty in what appears to be a single pulse. Other ecosystems declined gradually. Terrestrial forests thinned over what might have been thousands of years. Then, they collapsed suddenly in a secondary wave. This two-phase pattern is hard to explain with a single volcanic event. Volcanism is gradual. Even flood basalts take time. The effects build. You'd expect a steady decline as conditions worsened. Not this pattern of sudden collapses separated by time. The pattern is consistent with something else, though. A cascading industrial collapse. First, the cities fail. Infrastructure breaks down. Supply chains stop. People abandon urban centers. Agricultural systems fail next. Without fossil fuels, without transportation, without fertilizers and pesticides, food production crashes. Engineered ecosystems fail. The forests and grasslands that had been managed, altered, kept in artificial balance. They collapse when the management stops. Finally, the natural ecosystems fail, not from the collapse itself, but from the accumulated damage. The carbon in the atmosphere, the pollutants in the water, the temperature shifts. The chemical changes that had been building for centuries finally push natural systems past their breaking point. Two phases. First, the artificial systems, then the natural ones. We see the same pattern in simulations of modern civilization collapse. The ones where we model what happens if industrial society fails rapidly. Energy crisis, resource wars, climate feedback loops. The models show exactly this kind of staged collapse. Human systems fail first, natural systems follow. The Great Dying shows the same signature. If you compressed all known human history into a single breath, a pre-human civilization could have risen, conquered the planet, destroyed itself, and been completely forgotten in the time it takes to exhale. The Great Dying could be that exhalation, the moment when everything a species built came apart, when their atmospheric carbon triggered runaway warming, when their depleted oceans went anoxic, when their engineered ecosystems failed and took the natural world with them. The boundary layer would preserve only the chemical signature, the carbon spike, the isotope excursion, the sudden shift in ocean chemistry. It would look exactly like volcanism, because the end result is the same. You flood the atmosphere with carbon, you change the climate, you kill the oceans. Whether the carbon comes from volcanoes or factories doesn't matter to the rock record. The chemistry is identical. There's no smoking gun here, no proof, just a pattern that fits a little too well, an extinction that happened a little too fast, a boundary layer that could tell two different stories depending on what you're looking for. The Siberian traps are real. The volcanism happened, but volcanism might not be the whole story. It might just be the explanation we accept because the alternative is too strange to consider. The rock at the Permian-Triassic boundary is found all over the world. It's been studied for decades. The chemistry is well understood. The fossils below show a thriving world. The fossils above show a wasteland. And in between, there's just a thin layer of clay and carbon. Whatever happened, happened fast. Fast enough that the transition fits in a layer you can sometimes cover with your hand. That's all that remains of the worst catastrophe in the history of complex life. A layer of clay, an isotope signature, and the memory preserved in rock of a world that ended almost completely. We're creating a similar signature right now. The carbon we're releasing, the isotope ratios we're changing, the speed at which we're altering ocean chemistry. In 250 million years, someone might find a boundary layer marking our time. They'd see the carbon spike, the isotope excursion, the sudden shift in fossil assemblages. They'd propose a theory, volcanic activity perhaps, some natural catastrophe. They'd be measuring correctly, interpreting reasonably, and they might never consider that the boundary layer marks the moment a technological civilization used up its planet. The previous section ended with a boundary layer, a mark in stone that might represent us. 252 million years from now, some future geologist might find it and never know what really happened. 252 million years. Let's try to make that number mean something. Imagine each year of Earth's history is 1 mile of road. You're sitting in a car, driving backward through time at highway speed, 65 miles per hour. You're heading toward the Permian extinction, the moment 90% of life died. You start driving today. The trip computer calculates your arrival time. 442 years of continuous driving. No stops, no sleep, no breaks for fuel. You'd drive through the entire future history of the United States and keep going for 200 years beyond that, and you still wouldn't be halfway there. You'd need to keep driving for another 442 years. The founding of America would be ancient history by the time you arrived. Civilizations would rise and fall around your endless journey, and all of that time, all those centuries of driving, just to reach one extinction event, one boundary layer. That's not a long time in Earth's history. That's a medium-length time. The dinosaurs died 65 million years ago. The Cambrian explosion, when complex life suddenly appeared, happened 540 million years ago. The Oklo natural nuclear reactors in Gabon were operating 2 billion years ago. Earth itself formed 4.5 billion years ago. Each of these spans is vastly longer than the one to the Permian extinction. The time available isn't just deep, it's unfathomably deep. Try a different approach. Walking instead of driving. You can walk at about 3 miles per hour, not running, just walking. 1 year passes with each step. You start walking backward through time right now. In about an hour, you reach Rome, the founding of the Republic, the emperors, the fall. All of it happens in your first hour of walking. You keep going. 3 days later, you reach the invention of agriculture, the moment humans stopped wandering and started building cities. 3 days of walking. You're tired now, but you keep going. You walk for years, then decades, then centuries. To reach the dinosaur extinction, you'd need to walk for roughly 25,000 years. Modern humans have only existed for 300,000 years. You'd need to walk for nearly 1/10 of the entire span of human existence just to reach the dinosaurs, and that's still just 65 million years back. The Permian extinction is almost 4 times farther. You'd walk for nearly 100,000 years. Entire ice ages would come and go during your walk. Species would evolve and die around you, and when you finally arrived, you'd look back at where you started and realize the distance you've crossed isn't even 15% of Earth's total history. The past isn't close. It's isolated from us by a gulf that has no bridge. Even at the speed of light, the fastest possible speed in the universe, information from the Permian extinction would take 252 million years to reach us if time were distance. Nothing crosses that temporal gap instantly. Not light, not cosmic radiation, not anything. The past is genuinely, physically separated from us by an expanse that makes interstellar space look small. Here's another way to think about it. The surprise comes when you try to count. Start counting backward from today, 1 number per second. You count all day without stopping. You count through the night without sleeping. 1, 2, 3, 4. You keep counting. Days pass, then weeks, Then months, years go by. You're still counting. Your voice would fail, but imagine you could keep going. To count back 1 billion years, you'd count for 32 years straight. 32 years of numbers, 1 per second, 24 hours a day. That's longer than most careers, longer than many marriages. The dinosaur extinction happened 65 million years ago. To count back to that moment, you'd count for 2,000 years. 2,000 years. That's longer than Christianity has existed, longer than recorded history in most parts of the world. You'd start counting at the birth of Jesus and still be counting today, and you'd only be back to the dinosaurs. And here's the thing, you'd still have 187 million years to go to reach the Permian extinction. Another 6,000 years of counting. You'd count backward through the entire history of human civilization 3 times over and barely make a dent. The scale isn't just big, it's incomprehensible, even when you break it down to the smallest possible units. This is the time we're talking about when we ask whether another civilization might have existed before us. This is the canvas. Not thousands of years, not even millions, hundreds of millions, billions if we're considering the full history of Earth. Dinosaurs existed for 165 million years. That's longer than the entire span from their extinction to now. They had more time to evolve, to spread, to dominate every ecosystem than we've had since they disappeared. And they're just one group of animals during one era of Earth's history. Complex life has existed for over 500 million years. Simple life for more than 3 billion. Industrial human civilization is 200 years old. We're not even a rounding error. We're a flash, a boundary layer in the making, here for an instant, then gone into the fossil record, if we're lucky enough to leave one. All that time creates space, vast, empty space in the timeline where things could happen, things could rise, things could fall, things could vanish so completely that only the faintest traces remain, and only if you know exactly where to look and what to test for. When you try to feel the weight of deep time through driving or walking or counting, something becomes clear. There isn't just room for one previous civilization in Earth's history. There's room for dozens, hundreds maybe, each separated by tens of millions of years, each rising and falling in the geological instant we call an industrial period, each leaving behind a boundary layer that looks like a natural catastrophe, each disappearing so thoroughly that the next one would never suspect they existed. The question isn't whether there was enough time. There was more than enough time. The question is whether we'd recognize the evidence if we found it. Let's try a different kind of scale. Not distance this time, not speed, something closer to home. Your body. You have 2 parents, 4 grandparents, 8 great-grandparents. Every generation back, the number doubles. Go back 10 generations, 250 years, and you'd have over 1,000 direct ancestors if there were no overlap. 20 generations back, you'd have over 1 million. 40 generations back, about 1,000 years, you'd reach the time of the Crusades. And if every person in your family tree were unique, you'd have more than 1 trillion ancestors. 1 trillion individual people, each one necessary for you to exist. That's impossible, of course. Family trees converge. Cousins marry cousins. Lines fold back on themselves. But here's the thing that matters. 40 generations is nothing. That's 1,000 years. A blink. To reach the age of the dinosaurs, 65 million years ago, you'd need to count back 2.6 million generations. If every generation were a unique person, you'd have more ancestors than there are atoms in the observable universe. And that's just to reach the dinosaurs. Not even close to the beginning of complex life. We measure our lives in years, but maybe that's the wrong unit. Try heartbeats instead. Your heart beats about 70 times per minute. Every minute of your life, waking or sleeping, 70 pulses. In an hour, that's 4,200 beats. In a day, just over 100,000. In a year, about 36 million. If you live to 70, your heart will beat roughly 2.5 billion times. That's your entire existence. 2.5 billion moments of your heart pushing blood through your body. Every memory you have, every thought, every dream, All of it happened within those 2.5 billion beats. Picture this: every heartbeat represented by 1 second of silence. 1 beat, 1 second. Your entire lifetime would be about 80 years of continuous heartbeats laid end to end. Not bad. You could almost experience someone else's entire life measured that way. The Permian extinction happened 252 million years ago. To reach that moment using heartbeats as units, you'd need 10 billion lifetimes. Not 10 billion people. 10 billion full human lifetimes of continuous heartbeats. 10 billion times 2.5 billion. The Earth has beaten longer than that. The planet has a pulse we can't even begin to comprehend. This is the part that gets me. How long do you think it would take to breathe 252 million times? Not years, breaths. You breathe about 15 times per minute. Every minute, 15 cycles of air moving in and out of your lungs. In an hour, that's 900 breaths. In a day, about 13,000. In a year, roughly 5 million. Over a 70-year lifetime, you'll take approximately 550 million breaths. That's everything. Every word you speak, every song you sing, every sigh of relief or gasp of surprise, all within 550 million breaths. The Permian extinction is half a lifetime of breaths away. Half. You could breathe from birth to middle age, every breath representing a year, and you'd reach the moment when 90% of all species died. And that's just one event, one boundary in the rock. The Cambrian explosion happened 540 million years ago. That's an entire human lifetime of breaths into the past. Birth to death, every breath a year, and you still couldn't reach it. Think about that for a second. The scales we use to measure our lives, heartbeats, breaths, generations, they're perfect for human experience, but they shatter against deep time. They don't even dent it. There's something else, something that puts this in perspective. If you go back just 3,000 years, 120 generations, you reach a point called the genetic isopoint. That's the moment where you share at least one ancestor with every other human currently alive. Every person on this planet, all 8 billion of us, we're all genealogically connected within 3,000 years. We're family, distant, tangled, complicated family. But family, 252 million years ago? That's 10 million generations. Not of humans. Humans didn't exist. Of whatever lived then. Synapsids, proto-mammals, things with names like Lystrosaurus and Thrinaxodon. If intelligence arose during that time, if something built cities and machines and satellites, it would be more distant from us than we are from trilobites. We would have no genetic connection, no evolutionary relationship, nothing in common except the planet we happened to evolve on. They would be aliens who happened to live here. That's what deep time does. It doesn't just separate us from the past. It makes the past fundamentally other. An industrial civilization from the Permian wouldn't be our ancestors. They'd be unrelated. A completely different branch of life that rose, flourished, and vanished before the line that leads to us even began. We wouldn't recognize their biology. We wouldn't understand their chemistry. We might not even realize they were alive in the same way we think of life. And here's the thing that keeps me up at night. They could have been just as intelligent as us, just as capable, just as curious about their place in the universe. They could have asked the same questions we're asking now. Where did we come from? Are we alone? What happens when we're gone? They could have built monuments to their gods and equations to describe reality and stories to make sense of the darkness. And then they died, all of them, and the earth moved on. The continents shifted. The oceans rose and fell. New things crawled out of the ruins and started again. And none of them knew. None of them suspected. The new world had no memory of the old one. 12,000 generations back, 300,000 years, you reach the origin of modern humans, Homo sapiens, people who looked like us, thought like us, felt what we feel. That's when our story begins. 400 generations back, 10,000 years, agriculture starts. 40 generations back, 1,000 years, the Roman Empire is still a memory. 4 generations back, 100 years, and you're in the age of your great-grandparents. People some of us knew, people who held us when we were young. That's the scale we understand. 4 generations, maybe 10 if we're good with history, 20 if we really push. 2.6 million generations is beyond comprehension. It's not just big, it's other. It exists in a space our brains weren't built to navigate. We can say the words, we can write down the numbers, but we can't feel it. Not really. The best we can do is try to bridge from what we know, heartbeats, breaths, ancestors, to what we can barely imagine. And in that gap, in that vast space between what we can feel and what actually happened, there's room. Room for things to rise and fall. Room for intelligence to emerge, build, create, and vanish. Room for entire lineages of thought and culture to exist and disappear so completely that no trace remains except maybe a thin layer of carbon in the rock, a boundary layer, a statistical anomaly, something that looks natural until you know what to test for. The Earth has been beating for 4.5 billion years. That's 1.8 billion human lifetimes of heartbeats. 1.8 billion times you could be born, live, love, struggle, die. That's how long this planet has been here, patient, waiting, recycling itself over and over, grinding continents into the mantle and pushing new ones up, drowning coastlines and raising mountains, freezing into a snowball and thawing into a greenhouse. Again and again and again. We've been here for 300,000 years. Industrial civilization for 200. We're not even a breath yet. We're the inhale before the breath, the moment before the heartbeat. And we're trying to look back across 1.8 billion lifetimes and figure out if anyone else was ever here before us. That's the weight of the question. That's what we're actually asking when we talk about the Silurian Hypothesis. Not just whether ancient civilizations existed, but whether we could possibly know, whether information can survive that many heartbeats, that many breaths, that many generations of forgetting. So the question becomes, can information survive 1.8 billion lifetimes? Can anything last that long in a form we could recognize, let alone decode? There's a field called quantum archaeology. It's theoretical, speculative. Some physicists take it seriously. Others think it's wishful thinking dressed up in equations. The basic idea comes from quantum mechanics. Information, according to the laws of physics, is never truly destroyed, only dispersed, scrambled, spread across systems in ways that make it effectively impossible to retrieve. But the key word is effectively, not theoretically. Picture a mirror shattering. Thousands of pieces scatter across a floor. Each piece flies in a specific direction at a specific speed. If you could measure the position and momentum of every single fragment at the moment after impact, you could run the physics backward. You could watch the pieces leap back together in your equations. You could reconstruct the mirror perfectly, the information about what the mirror was, how it broke, even what reflected in it at the moment of shattering. All of that is preserved in the trajectories of the shards. Theoretically possible according to physics, practically impossible with our technology, but the information never truly disappears. That's quantum archaeology. The idea that if you could map the complete quantum state of a system down to every particle, you could reconstruct its past states. You could rewind time mathematically. The problem is scale. To reconstruct anything meaningful, you'd need to track billions of particles. You'd need to know their positions and momentums simultaneously, which violates the uncertainty principle. You'd need computational power that doesn't exist and won't exist for centuries, if ever. You'd need to account for every interaction those particles had with every other particle in their environment. The measurement alone would require more energy than the thing you're trying to measure. But here's what matters for our purposes. The information exists, degraded, dispersed, corrupted, but present. Think about it this way. Imagine you burned a book and scattered the ashes across a continent. The book is gone, no question. But every ash particle contains information about the paper, ink, and binding. Carbon isotope ratios tell you what plant the paper came from. Trace elements tell you about the ink composition. Calcium and other minerals tell you about the binding materials. If you could collect every single particle and analyze it precisely enough, You could reconstruct the text. You'd need to know the paper chemistry, the ink formula, the printing process. You'd need to map how combustion altered each molecule. You'd need to trace where wind carried each particle. The scale makes it impossible, but the information exists. Geological formations are worse, much worse. A rock that's been buried, heated, compressed, partially melted, thrust back to the surface, weathered, and buried again. That's not a scattered book. That's a hard drive that's been smashed, buried, heated, compressed, and partially melted. But even a destroyed hard drive retains faint traces of data in its magnetic domains. Even a melted circuit board preserves patterns in how the silicon crystallized. You'd need to know what codec the original civilization used, what file format, what language, what medium they stored information on. But the data is there, corrupted but present. The question isn't whether information survives geological time. It does. The question is whether enough survives in a concentrated enough form that we could recognize it as information rather than noise. DNA survives in fossils for up to 1 million years. That's our current record. 1 million years of chemical bonds staying intact in the right sequence to be readable. Proteins survive longer, up to 4 million years. They're simpler molecules, more stable. 4 million years is long enough to span the entire existence of our genus. Every human ancestor back to the first Homo species could theoretically leave protein traces we could sequence. But 4 million years is nothing on geological time. 4 million years ago, the Pliocene epoch was ending. The Earth was entering the Ice Age cycles that would shape human evolution. 4 million years is less than 1/10 of 1% of Earth's history. Crystal structures, though, crystal structures are different. Minerals form in layers. Atoms lock into repeating patterns. Those patterns can trap other molecules inside them, like insects in amber, but at the molecular scale. And crystals are stable, really stable. Once a crystal forms, its internal structure resists change. Heat can alter it, pressure can deform it. Chemical reactions can replace some atoms with others, but the basic lattice pattern, the arrangement of layers, the spacing between atoms, the distribution of impurities, that persists. Certain clay minerals have layered crystal structures that work like molecular archives. Montmorillonite, kaolinite, elite. These clays form from the weathering of volcanic rock. They're everywhere, and their crystal layers can trap organic molecules between them, preserving the molecular structure for hundreds of millions of years. In 2017, researchers found organic compounds preserved in 3.5 billion-year-old rock from Australia. Not fossils, actual molecules, locked in crystal matrices, 3.5 billion years. That's before photosynthesis, before atmospheric oxygen, before anything we'd recognize as complex life, and the molecules survived. Let that sink in. If simple organic molecules can survive 3.5 billion years, if carbon chains and ring structures can remain intact that long when trapped in the right mineral matrix, then more complex information structures could theoretically survive as well. Information encoded in crystal patterns. Information encoded in the distribution of rare earth elements. Information encoded in isotope arrangements that don't match natural processes. The planet itself might be a library, and we don't know the language. We don't know the filing system. We don't even know what the books look like. We're archaeologists in an alien archive, and everything looks like random stone. You'd need to know what to look for, what patterns indicate information versus noise, what mineral formations could preserve technological signatures, what crystal structures might encode data intentionally versus accidentally. We barely know how to read the natural geological record. We're still arguing about what certain rock formations tell us about ancient climates and ocean chemistry. We're still discovering new ways that biological activity leaves traces in stone, and we're looking for signals we understand: photosynthesis, oxidation, decomposition, natural processes. What would an artificial signal look like after 100 million years? After 500 million? After 1 billion? We don't know. That's the honest answer. We have theories about information preservation. We have examples of molecules surviving impossible spans of time. We have physics that says information can't be destroyed. only dispersed. But we don't have a roadmap. We don't have a search pattern. We don't have a way to distinguish a billion-year-old data storage medium from a random chunk of metamorphic rock. Unless we know what specific structures to look for, unless we can identify formations that shouldn't exist naturally, unless we find something concentrated enough, preserved enough, anomalous enough that it stands out against 4.5 billion years of geological noise. That uncertainty, that inability to read the geological record for artificial signals, that's actually the optimistic problem. That's the problem you face if something survived to be found. There's a more fundamental issue. Most structures don't survive at all. Let's start above our heads, in orbit. Imagine a civilization launches satellites, builds space stations, creates an infrastructure network around their planet. Surely those would last, right? No weather in space, no erosion, no rust, just the endless dark and the cold. Not quite. A satellite in low Earth orbit, anything below about 600 kilometers, experiences atmospheric drag. The atmosphere doesn't just stop at some clean boundary, it fades gradually. Even at 400 kilometers, where the International Space Station orbits, there are still wisps of gas, thin enough that you'd call it vacuum in any Earth laboratory, but enough to create friction against something moving at 8 kilometers per second. That friction produces heat. Heat bleeds energy. Energy loss means the orbit decays. The satellite drops lower. The atmosphere gets thicker. The drag increases. The process accelerates. A satellite in low orbit lasts decades at most, sometimes just years. Medium Earth orbit is better. Between 2,000 and 35,000 kilometers, satellites can persist for millennia. The atmosphere is gone. The drag is negligible. These orbits are stable on human timescales. Geostationary orbit, 35,786 kilometers up, where satellites match Earth's rotation. That's even more stable. A satellite there could last millions of years. The orbit isn't perfectly stable. Gravitational perturbations from the moon and sun cause drift. Over enough time, everything falls or escapes. But we're talking geological timescales now. Here's the strange part. A spacecraft in low orbit lasts decades. A city on the ocean floor lasts maybe 10,000 years before sediment buries it, and 100 million years before the entire section of ocean floor gets pulled into the mantle and melted. The satellite outlives the city. Your entire civilization's space infrastructure remains in orbit longer than the ruins of your capital city remain on Earth. Think about that. The ocean floor feels permanent. Solid rock, the foundation of the world. It's not. It's the youngest part of Earth's crust. The oldest ocean floor anywhere on this planet is roughly 200 million years old. That sounds ancient. In geological terms, it's recent, and the Atlantic Ocean floor is younger than the last dinosaurs. Ocean floor gets created at mid-ocean ridges. Magma wells up from the mantle, cools, solidifies. The new rock pushes the old rock aside. The ocean floor spreads. The continents drift. This happens slowly, a few centimeters per year, about the speed your fingernails grow, but it never stops. The ocean floor spreads away from the ridges and eventually reaches a subduction zone. One tectonic plate slides beneath another. The ocean floor gets dragged down into the mantle. The pressure increases. The temperature rises. The rock melts. Everything on that section of crust, sediment, fossils, minerals, structures, goes into the mantle and becomes magma again. The average lifespan of ocean floor is 100 to 200 million years. Then it gets recycled. If an ancient civilization built cities underwater, chose the ocean depths, for some reason we can't imagine, those cities are gone. Not buried, not eroded, melted. The ground they stood on no longer exists as ground. It's liquid rock beneath our feet, waiting to erupt from some volcano and start the cycle again. Surface structures don't fare much better. Mountains feel eternal. They're the symbols we use for permanence, for things that endure. We carve faces into them expecting them to last. We build monuments on peaks because height means significance, visibility, immortality. The Himalayas are 50 million years old. They're tall, the tallest mountains on Earth. They're also eroding, fast. The monsoon rains hammer them, rivers carve through them, glaciers grind them down, landslides strip away entire slopes. In another 50 million years, they'll be significantly smaller. In 100 million years, they might be hills. The Appalachian Mountains are older, about 480 million years old. When those mountains were young, they were as tall as the Himalayas are now, towering peaks scraping the sky. They've been eroding for 500 million years. They're gentle now, rolling hills covered in forest. Beautiful, but nothing like what they were. Here's the thing that gets me about the Appalachians. If a civilization existed when those mountains were young and towering, if they built cities into those peaks, carved monuments into those cliffs, nothing would remain. All evidence has been worn away, crushed to sediment, washed to sea, subducted into trenches, melted in the mantle. The mountains themselves have been recycled. The rock that forms them now isn't the same rock that formed their peaks 400 million years ago. You could have carved faces a mile high into those peaks. They'd be molecular dust by now. Imagine building a monument meant to last forever. You choose the hardest stone, solid granite. You place it on a mountaintop, high above the erosion of valleys. You make it massive. A pyramid, a tower, a carved mountain itself. You engineer it to resist earthquakes, to shed water, to endure. Within 10 million years, the mountain has eroded. The monument is gravel. The gravel has washed into rivers, been carried to the ocean, settled into sediment layers, been compressed into rock, been subducted into a trench, and melted back into the mantle. Permanence is an illusion on geological timescales. Scientists have terminology for everything happening here. Thalassology for the study of ocean floors, plate tectonics for the movement of crustal plates, subduction for the process of one plate diving beneath another, orogeny for mountain building. They have names for erosion, weathering, sedimentation, metamorphism. They have names for every process that shapes and reshapes the crust. They don't have a name for the study of structures that no longer exist because the ground they were built on was recycled into magma. Maybe they should. We could call it futility geology. That's dark, but it's accurate. Earth is a recycling machine. The crust is temporary. The surface is temporary. Everything solid is temporary if you wait long enough. The mantle churns. Plates move. Mountains rise and fall. Ocean floors spread and subduct. The conveyor belt never stops. This creates a detection problem. You're not just looking for traces of a civilization millions of years gone. You're looking for traces on a planet that actively destroys its own surface, that melts its ocean floors every 200 million years, that grinds its mountains into dust, that buries, compresses, heats, and melts layers of rock in an endless cycle. Even if a previous civilization built structures designed to last, Earth doesn't care about design specifications. The forces at work operate on scales that dwarf engineering. A subduction zone doesn't notice your reinforced foundation. Erosion doesn't spare your monument valley because you carved it from solid stone. The question isn't whether ancient structures could survive. The question is whether anything could survive, whether there's any configuration of matter that can persist as a recognizable structure through 100 million years of geological recycling. The answer is probably no. Not intact structures, not cities or buildings or monuments. Those are gone. But maybe fragments survive. Maybe trace elements concentrate in unusual ways. Maybe certain formations resist subduction, get scraped off the descending plate, accrete onto continents. Maybe some materials end up in geological contexts that preserve them not as structures but as anomalies, concentrations that shouldn't exist, ratios that don't match natural processes. That's what we're looking for. Not ruins, anomalies. We've been looking backward, looking for traces of something that came before, searching the rocks for anomalies that don't fit, for patterns that shouldn't exist. But there's another way to approach this question. Turn the lens around. Look at what's happening right now. Look at us. We are currently running the exact experiment the Silurian Hypothesis describes. We're creating technosignatures in real time, testing which ones will survive deep time. We're the control group. In 100 million years, will something find our layer and wonder, What we were? The answer is almost certainly yes, because we're leaving traces everywhere. Start with the atmosphere. Carbon dioxide levels right now sit at about 420 parts per million. That's the highest concentration in 3 million years. Before the Industrial Revolution, before we started burning coal and oil, that number was 280 parts per million. We've added 140 parts per million in about 200 years. That's not just high, that's fast. Faster than any natural event recorded in ice cores going back 800,000 years. When you pull an ice core from Antarctica, you can see atmospheric history preserved in tiny air bubbles. The carbon record looks stable for hundreds of thousands of years. Then suddenly, at our moment, it spikes, a vertical line on the graph. Every time you drive a car, you're adding ancient carbon to the atmosphere. Carbon that was locked underground for millions of years, now released in seconds. That carbon has a signature. It's isotopically different from carbon that cycles naturally through plants and animals. We can detect it. Future geologists will detect it too. It will appear in ice cores, if ice survives, in ocean sediments, in the shells of marine organisms, in limestone that forms from those shells. You are personally contributing to the geological record. Your commute will outlast your civilization. That's not abstract. That's chemistry. Carbon with our fingerprints on it, spreading through every system on Earth. Then there's plastic. Over 8 billion tons produced so far. Much of it now breaking down into microplastics in the ocean. Tiny fragments suspended in seawater, settling into sediment, being consumed by organisms whose shells will eventually become rock. Plastic doesn't biodegrade on human timescales. It fragments, but it doesn't disappear. Those polymers are synthetic. They don't occur naturally. A geologist 100 million years from now, examining ocean sediments from our time, will find a layer full of weird hydrocarbon chains that shouldn't exist. Chains that only form in industrial processes. They'll know something made those. Something that understood chemistry. Concrete is another signature. We produce about 4 billion tons annually. 4 billion tons. That's enough to cover every square meter of land on Earth with a layer about the thickness of a coin. Every year. Concrete is made from limestone, heated to extreme temperatures, then mixed with specific additives. It has a distinctive chemical composition. It will leave a layer in the geological record, a boundary where suddenly, in certain locations, you find this strange calcium silicate material concentrated in formations that look like they were poured. Because they were. The urban heat signature adds another trace. Cities create measurable temperature anomalies. Concrete and asphalt absorb heat differently than soil or vegetation. That heat affects local rock chemistry. Minerals form differently at different temperatures. A future geologist might find chemical variations in rock layers that correspond to where cities used to be. Thermal ghosts of our infrastructure. Agriculture leaves nitrogen isotope signatures. We use synthetic fertilizers made from atmospheric nitrogen. That nitrogen has a different isotope ratio than nitrogen cycling naturally through ecosystems. It appears in soil layers, in runoff that reaches the ocean, in sediments near river deltas. The signature says, something was concentrating nitrogen artificially. Something was farming. If an archaeologist from 100 million years in the future digs through rock to our time, they'll find a layer of concrete, plastic microparticles, chicken bones. We've bred so many chickens, they'll be the most common fossil. And radioactive isotopes that don't occur naturally. They'll call it the Anthropocene boundary, the layer where humans happened. That last one deserves attention. There's a proposal to define the beginning of the Anthropocene epoch at July 16th, 1945, the date of the first atomic bomb test. The Trinity test in New Mexico. That moment scattered radioactive isotopes across the planet. Fallout from that blast and the tests that followed reached every continent, every ocean. Isotopes like plutonium-239 and cesium-137 don't occur naturally in surface environments. They're created in nuclear reactions. They're detectable in ice cores, in sediment cores, in tree rings from that era forward. Depending on the isotope, they'll remain detectable for thousands to millions of years. Human civilization crossed a threshold that day. We became detectable from space and in deep time. Before 1945, an alien geologist might miss us. Our impact was significant, but maybe subtle, maybe erasable by time. After 1945, we're impossible to miss. We announced ourselves to the universe and to the future in the same instant, and we did it with a weapon. Think about that for a second. Our most permanent mark isn't art or architecture or literature. It's radioactive contamination. The thing that will outlast everything else we've made is the residue of weapons tests. That's our iridium layer. That's our boundary marker in the rock. If we're looking for previous industrial civilizations, we're looking for traces like these. Anomalies in isotope ratios, concentrations of synthetic materials, chemical signatures that don't match natural processes. We know these things persist because we're creating them right now. We're watching them spread through the environment. We're measuring them. We're documenting our own fossilization. This isn't speculation. This is observation. We are the civilization that might become invisible. We're experiencing in real time what the Silurian Hypothesis proposes happened before, and we can see how difficult it is to leave a lasting mark, how quickly natural processes begin erasing our work. Erosion starts the moment we build something. Concrete cracks and weathers, plastic fragments and disperses. Even our radioactive isotopes decay, becoming less detectable with every passing century. In 100 million years, most of what we've built will be gone, but the layer will remain. The boundary, the chemical anomaly. Future geologists might find that layer and debate what it means. They might argue about whether it represents a civilization or just a strange natural event. They might miss it entirely if they're not looking in the right places, because Earth doesn't preserve things. Earth recycles. The odds are always against detection, but we exist, we happened, and we've left traces that will persist long after every human is gone, long after our cities crumble, long after our species is forgotten. The chemistry remains, the isotopes remain, the layer remains, which means if someone else did this before us, their layer might remain too, somewhere, compressed in rock we haven't examined, subducted and melted, but with fragments scraped off and preserved, or buried under ice in Antarctica, waiting. The question isn't whether they could leave traces. We know they could. We're doing it. The question is whether anyone will recognize those traces for what they are, whether the pattern is visible after deep time grinds it down to chemical noise. We're writing ourselves into the rock right now. One car trip, one plastic bottle, 1 ton of concrete at a time, creating the fossil record of our existence, testing whether industrial civilization can survive as anything more than a rumor in the stone. We've already built things meant to outlast us. The Voyager spacecraft will orbit the galaxy for billions of years, carrying messages from humanity. We've carved warnings into granite about buried nuclear waste. We've launched time capsules. We understand the impulse to speak across time. An ancient civilization would have had the same impulse, just a longer timeline and perhaps better technology. Think about nuclear waste. We bury radioactive material that stays lethal for 10,000 years or more. 10,000 years is longer than recorded human history, longer than agriculture, longer than cities. How do you warn people that far in the future about invisible danger buried underground? They won't speak your language. They won't recognize your symbols. They might not even have the same concepts of danger or death. Researchers have proposed solutions. Durable monuments carved with warnings in multiple formats. Landscapes engineered to feel hostile and wrong. Even an atomic priesthood, a cultural institution that preserves the knowledge of buried waste across generations through ritual and tradition. The goal is simple. Make sure someone in the year 12,000 knows what we buried in the year 2000. That's 10,000 years. The Silurian Hypothesis asks us to think about timescales 1,000 times longer. 100 million years. What could possibly survive that long and still deliver a message? Imagine a lighthouse keeper whose shift never ends, still turning on the light every night even though no ships have passed in eons. That's what a guardian system would be, an automated technology waiting for the next intelligence to arise, still faithfully executing its protocol after 100 million years, checking the sensors, running the diagnostics, keeping the message ready, waiting. Could something like that actually exist? Could it survive? The environment is the problem. Voyager will last billions of years because it's coasting through empty space. No weather, no earthquakes, no erosion, just cold vacuum and occasional dust. But a guardian system on Earth would need to survive plate tectonics, ice ages, asteroid impacts, oxygen in the atmosphere corroding everything metal, water seeping into every crack, life consuming anything organic. You can't build that from steel or silicon. Those materials decay, rust, fracture, break down into constituent elements and wash away. The information would need to be encoded differently. Geological structures arranged in mathematically significant patterns, crystal formations that don't occur naturally, magnetic anomalies positioned with astronomical precision, isotope distributions in rock that spell out prime numbers when you measure them correctly. Not a machine in the traditional sense. Something weirder, something that uses the planet itself as the medium. We might have already found these things. We'd catalogue them as curiosities, publish papers on the interesting natural formation, note the unusual regularity, propose some geological process we don't fully understand, and move on, never realizing we'd found an answering machine with 100-million-year-old voicemail. What if some geological formations aren't natural? What if certain precisely aligned magnetic anomalies or strangely regular crystal structures or mathematically significant isotope distributions are messages we haven't learned to read? There's another possibility, a guardian system that left Earth entirely, von Neumann probes. That's the technical name, theoretical self-replicating spacecraft that could explore the galaxy indefinitely. You send one out, it reaches another star system, mines asteroids for materials, builds copies of itself. Those copies fly to other stars and repeat the process. One probe becomes two become four. Eventually, you've explored the entire galaxy without ever leaving home. If an ancient terrestrial civilization achieved spaceflight before their collapse, those probes could still be operating, mining asteroids in our solar system, orbiting Jupiter's moons, sitting dormant in the Kuiper Belt, waiting for the next technological species to develop radio telescopes. They wouldn't need Earth to survive. They'd be self-sufficient, self-repairing, patient. We wouldn't recognize them if we saw them. We'd classify them as asteroids with unusual orbits, comets with strange outgassing patterns, natural objects with curious properties. It takes incredible resolution to image anything beyond Mars. We've barely begun to catalogue the objects in our own solar system. There could be 1,000 ancient probes out there, and we'd never know. The difference between Voyager and a guardian system is the mission profile. Voyager is passive, a message in a bottle. It carries information but doesn't seek anyone out. A guardian system would be active, waiting for specific conditions, monitoring for signs of new intelligence, ready to respond when triggered. The WOW signal, 1977. Ohio State University's Big Ear radio telescope detected a strong narrowband radio signal from space. It lasted 72 seconds. The astronomer on duty was so surprised he wrote, "Wow," in the margin of the printout. That's how it got its name. The signal never repeated. We've searched the same patch of sky for 46 years. Nothing. Silence. We've assumed it must be extraterrestrial because nothing on Earth transmits that way. But what if it's terrestrial, just not from our civilization? What if it's an ancient guardian system that activates periodically, and we happen to be listening during one of its rare transmissions? 46 years is nothing if the transmission cycle is measured in centuries or millennia. We're not patient enough to detect it again. We expect answers on human timescales, but a guardian system thinking in geological time wouldn't care if we're listening. It would broadcast on schedule, every 500 years, every 1,000, every 10,000, faithfully executing its protocol, waiting for someone to be ready to understand. We wouldn't know if we'd been warned. We wouldn't know if something was trying to help us avoid their mistakes. The message could be there, repeating endlessly, and we'd classify it as an anomaly, an interesting natural phenomenon. Space weather we don't quite understand. Or maybe there's nothing. Maybe civilizations don't build guardian systems because there's no point. Once you're gone, you're gone. Why spend resources trying to talk to a future that might never come? Why assume the next intelligence will need your warnings or want your guidance? But we built Voyager. We carved warnings into granite. We launched time capsules knowing full well they might never be found, knowing they might be found by something we can't imagine. We did it anyway, because the impulse to reach across time is deeper than logic. It's the same impulse that makes us carve our names in trees, leave handprints on cave walls, write letters we'll never send. We want to be remembered. We want to matter. We want to say we were here. An ancient civilization would have felt the same thing. That's not speculation. That's human nature, or whatever their equivalent was. If they had time to prepare, if they saw their collapse coming, they would have tried to leave something behind, some way to say, this is what we learned. These are the mistakes we made. This is how you might do better. The question is whether we're listening in the right way, whether we've learned to read their language, whether we're patient enough to hear a message transmitted once every 1,000 years, whether we can recognize a guardian system when it's staring us in the face. We catalogue the anomalies, we note the curiosities, we file them away as problems to solve later. Maybe some of those problems aren't natural. Maybe they're answers to questions we haven't learned to ask yet. Let's be honest about what we actually have here. No confirmed technosignatures older than human civilization have been found. Not one. Every anomaly we've discussed has a plausible natural explanation. Every single one. That's not a weakness in the hypothesis. That's exactly what the hypothesis predicts. But it does mean we're working with absence, not presence. The Silurian hypothesis faces a fundamental problem. The scientific method requires falsifiability. A hypothesis must be testable. It must be potentially disprovable. You need to be able to say, here's what would prove this wrong. The Silurian hypothesis is arguably unfalsifiable because the null hypothesis and the actual result produce the same observation. Nothing. No ancient civilization existed, or an ancient civilization existed but left nothing detectable. Both scenarios look identical. Nothing remains either way. That doesn't make it unscientific. It makes it a hypothesis about the limits of detection. Science isn't just about finding answers. It's also about understanding what questions we can't answer and why. The Silurian hypothesis is, at its core, a question about epistemology. How do we know what we think we know about deep time? What can we actually claim with confidence when 99% of the evidence has been destroyed? To confirm the hypothesis, we'd need something specific, distinctive isotope ratios with no natural explanation, synthetic compounds that don't occur naturally and somehow survive long enough to detect, or structured information in geological formations, a pattern that couldn't arise from natural processes, something unambiguous, something that screams intelligence instead of whispering possibility. The problem is our detection limits. Our deepest ice cores reach back 800,000 years. That's in Antarctica, where ice accumulates and compresses and preserves atmospheric bubbles like a time capsule. 800,000 years sounds like a lot. It's roughly 4 times longer than modern humans have existed. But beyond that mark, no direct atmospheric record exists. None. We lose the ability to sample ancient air. Ocean sediment cores go back further, much further, but with less resolution. The detail blurs. You're looking at averages across thousands of years instead of snapshots of individual centuries. It's like trying to read a book where every page has been sanded down until only the general shape of paragraphs remains. You know something was written there. You just can't make out the words. The most detailed geological record covers the past 500 million years. Before that, most rocks have been metamorphosed or subducted. They've been cooked by heat and pressure until their original structure is gone, or they've been dragged down into the mantle and recycled into new crust. The evidence doesn't just fade, it gets destroyed and rewritten. Anything older than 500 million years is extremely difficult to assess. Anything older than 2 billion years is nearly impossible, except through chemical signatures in surviving rock. You're not looking for objects anymore. You're looking for the ghost of objects, the chemical shadow they might have left behind. Trying to detect a 100 million-year-old civilization is like trying to prove your great-great-great-grandparents existed. But all records were lost, their house was demolished, the city was bulldozed, a forest grew over it, the forest fossilized, and now you're looking at coal trying to find their signature. Theoretically possible. Practically? Good luck. We're very good at assuming we're special. First, we thought we were the center of the universe. Wrong. Then we thought our sun was special. Wrong. Then our galaxy. Wrong. Then our planet as the only life. Probably wrong. Now we assume we're the first civilization on our own planet. You'd think we'd learn to be more humble, but here we are, still assuming we're the exception. The honest answer is we're looking for something we wouldn't recognize if we found it, using methods designed to find natural processes in a record that's 99% destroyed. It's not impossible. It's just really, really difficult. Maybe impossibly difficult. We don't know where that line is yet. What would falsify the hypothesis? Finding evidence that the geological record is more complete than we thought. Discovering that certain types of artifacts or chemicals should survive longer than current models predict, and then not finding them. That would be meaningful absence. Right now, we have expected absence. There's a difference. The questions that remain are bigger than just, did an ancient civilization exist? They're about what we can know at all, about the limits of inference when time itself erases the evidence, about whether some questions are simply unanswerable, not because we lack the tools, but because the information no longer exists in any form. We catalogue anomalies, we note curiosities, we file them as natural until proven otherwise. That's the right approach, that's good science. But it also means we might be staring at answers without recognizing the questions. Or recognizing questions we'll never be able to answer. The Silurian Hypothesis doesn't claim there was an ancient civilization. It claims we wouldn't know if there was. And maybe that's the most honest thing we can say about deep time. We've spent this entire journey asking whether there might have been civilizations before us. Ancient industrial societies that rose and fell and left almost nothing behind. The Silurian Hypothesis doesn't answer that question. It reframes it. It asks us to consider what it means to exist in deep time, to build something knowing that time itself will erase it. Here's what we know for certain. Human industrial civilization is roughly 200 years old. That's it. 2 centuries of burning fossil fuels and reshaping continents and launching satellites. In geological terms, we haven't even started. We're a blink. A whisper. We could vanish tomorrow and leave almost no trace in the rock record. A thin layer of strange chemistry, some plastic particles, maybe a few isotopes that shouldn't be there. That's all, but we're still here, still writing our chapter, and the question that matters isn't whether someone came before us. It's what we do with the time we have. Every species that ever lived is a rough draft of intelligence. Evolution kept writing, kept revising, and we're just the version that happens to be reading the manuscript right now. We don't know if we're the final draft or just another revision that gets crumpled up and thrown away. The only way to find out is to keep writing, to see if our chapter has an ending or just trails off mid-sentence. The Silurian Hypothesis reframes humanity not as the pinnacle of Earth's history, but as a chapter in a book we didn't write and might not finish. Whether we're the first chapter about intelligence or the 15th, the responsibility is the same. Don't be the chapter where the story ends. Right now, we're creating exactly the kind of evidence we've been looking for. Atmospheric changes matching the fastest natural climate shifts on record, biodiversity loss comparable to mass extinctions, resource depletion accelerating. We are, in real time, writing ourselves into the geological record, leaving a boundary layer that future geologists might puzzle over, the same way we puzzle over ancient anomalies. They might find our plastic and our concrete and our isotopes and wonder what happened, why it stopped, or maybe they won't. Maybe we'll be the first to make it through, the first civilization on Earth to achieve sustainability, to stabilize our impact, to spread beyond this single planet and ensure that our story doesn't end with a thin layer of strange chemistry. Here's the thing that might matter most. If we succeed, If we make it through the next 1,000 years and beyond, we'll be doing something that might be extraordinarily rare, even on our own planet. Success isn't guaranteed by evolution or intelligence. The fossil record shows that most species fail. Most lineages go extinct. If intelligence arose before us and failed, that tells us something crucial. Being smart isn't enough. You also have to be wise. And wise is harder. Earth is a palimpsest, a manuscript where old text is scraped away so new text can be written, but traces of the original remain underneath. If there were civilizations before us, we're writing over their story. And someday, something might write over ours. The question is, what do we want that faint, barely readable trace to say? That we existed and burned brightly and vanished? Or that we existed and learned and endured? We might be the first. We might be the last. We might be one in a long series of attempts by this planet to produce something that lasts. We don't know, but the uncertainty doesn't erase the responsibility. It amplifies it. Remember those metal spheres from the beginning, 2.2 billion years old, sitting in a museum in South Africa. Probably natural, almost certainly natural, but strange enough to make us wonder. Right now, we're leaving our own spheres, our own anomalies, things that will make future beings wonder what we were and what happened to us. The difference is, we get to decide what the answer to that second question will be. We're not fossils yet. We're still writing. The Silurian Hypothesis isn't about ancient civilizations. It's about time and evidence and the limits of what we can know. But it's also about us, about recognizing that we're not outside of deep time. We're in it. We're subject to the same forces that erased everything that came before: erosion and subduction and the slow churning of continents. The only question is whether we'll be a cautionary tale or something else, something new. That choice is still ahead of us, still unwritten. And maybe that's the most important thing the Silurian Hypothesis teaches us. Not that we might find evidence of lost civilizations, but that we're creating evidence of our own right now. And we still have time to decide what that evidence will say about us, whether it will speak of wisdom or just intelligence, of endurance or just existence. The manuscript is still open, time is still writing, and we're holding the pen.